Okay, welcome to today is the 29th of September. We're scheduled for an exam on the 13th of this month, this coming month, basically October. Okay, October 13th. Originally, it's supposed to cover chapters 1 through 18, but because of the fact that we're a little behind, I think we're a week or 2 weeks, week and a half, I think, behind in the schedule. So we're not going to do that. We're going to keep the exam on the 13th, which is a Tuesday. But instead, we're going to cover all the way to chapter 14. Thermodynamics is not going to be included, and heat transfer and all of that is not going to be included. So chapters 1 through 14 is going to be part of the exam. So we're changing a little bit the order in terms of how these exams are. So it's a little bit less materials for you to cover. There will be, again, it's going to be based on the questions that we're going to be doing something like the homework. So you're going to have questions, you're going to be during the lecture time. And so we'll start the exam around 4 o'clock, but it's not going to end at 25? So we will need more time because some of you probably need to get off work. So it's going to end sometime in the evening, allowing for the people to leave from work and come and do their exam. The exam itself should take about an hour and a half. Okay, so if you start at 4 o'clock, by 5:30 you should be done with it. I would allocate about half an hour. Yes. Okay. Question from Kyle: is it one attempt? Yes. Okay. So basically, I will allow about half an hour for you to figure out how to submit your answers. They should be really on Canvas, so you should not have difficulty with it. But making sure you go through your answers, analyze them, check them, make sure that everything you do is correct. So you will have about 2 hours, maybe to for the entire exam. So once you start it, you should not really leave. Since Kyle asked that question, you should not really leave until you're done with it. Okay. So that's basically how the process is. So if you know that you're going to be late that day because you're working and the boss would not let you out until 5:30, for example, do not start it, and then come back later on for it because the attempt will be done. No V. It's not going to be multiple choice. It's going to be fill in the blanks. Okay. Type of the homework. So that's basically how it is. Quizzes are different than the exams. So again, you will have review materials for it, and you should be ready basically all the chapters from 1 through 13. 14, okay? So the content should be, at this point, I did not decide Waze again, so it's going to be tailored so that it takes you, Waze is asking how many questions. It's going to take about an hour and a half for you to finish the exam. To be exact, an hour and 25 minutes. So it needs to be timed for me. So basically to take that much time to cover it. So at this point, the number of questions is still not determined yet, depending on the level of work that needs to be going in each and every one of them. Okay. But again, you're going to get more details down the road. I mean, we're about 2 weeks away, so it's not that long. So next week, you will have more details into how this is going to be structured. By then, I expect chapter 14 will be completely covered. On Canvas right now, you have chapter 11 through 14 basically available for you guys. So you should have everything. Come chapter week of the exam, you should not have any other assignments. Yes, it is going to be due by the evening on that day, the 13th, okay? So you start on the, it is the 13th when the exam originally was supposed to start? Let me check the schedule, okay, again. I want to make sure I give you the correct information at this point. Yes, October 13th. That's where the midterm is. So there is a slight change in the order of the questions, basically. And it's not going to cover anything after chapter 14. However, that doesn't mean that chapter 15, for example, is not important, because it's going to come back later on when we do the other exam. Okay. So that's in a nutshell something that to look forward to get you ready for it. For those who are not here, they will be watching the recording, and hopefully they will follow this one in here and also pick up the information. You have had also in the last week on chapter 10, you have had a discussion. Some of you already submitted the answers, others did not. Note that there are two parts to this discussion, as I promised. The first part, which is some of you already have submitted, namely the measurements for A, B, and C. Okay, for the different ellipses that they have basically formed following the instructions, okay? Then you're supposed to go back and calculate the ratio of C over A. Let me make sure that that's a question, okay? Not yours, somebody else, okay? Don't calculate the one that is for you. So you calculate this ratio of C over A, okay? And if that number is very small, like 0.1 or 0.2, then you know the shape is more or less a circular shape. You can look at the picture. If they submitted the picture and tell them, okay, it confirms that it's a circular shape. But it's very close from 1. Let's say, for example, 0.9. Then you tell them that the shape that you drew actually corresponds to your measurements. So in a sense, you're confirming their data. I went back to the discussion and I added, as I promised, the formulas to use. So there are two components to it, two parts to it. The first part, you submit your own data for A, B, and C. And if you can, please include a picture of your own drawing. Okay, that's one part. The second part, you go back to somebody else, okay, not yours, and you calculate C over A. It should be a number. It should not have dimensions. It should not be centimeters or grams or kilograms. It's a number, okay? Because if C is measured in inches and A is in inches, the inch cancel the inch and we're done. If it's in centimeters, the centimeter cancels the centimeter and we're done. So it's going to be a number between 0 and 1, okay? If it's closer to 0, the shape is circular. If it's closer to 1, the shape is very flat, almost a line, okay? So that's the eccentricity measures how flat your ellipse is, basically. That's the value to look for. Yes, Wace was asking about the assignments. As I promised also, I dropped the lowest grades, so I changed the formula. So some of the grades that were lowest automatically are dropped by Canvas now. Okay, so I applied the formulas already for the discussions too. For the quizzes and the other things, the lowest one. Please do not assume that this is the one that you're going to drop, because you might end up with a more difficult one, more difficult task, and you will end up with a problem. They're saying, oh man, I should have done the other one, which is probably better for me than this one. So do not make any assumptions. Take everything seriously. Do not think that this is the quiz I'm going to drop, so I'm not going to do. Then the next one probably will have it even harder. And now you have one that you dropped that you could have done well in it, and another one that you didn't do well in it. So do not come with that attitude. That's actually a negative attitude, and it's really not helpful in my thinking. You have a justified excuse, for example, sick, or you cannot make it, or traveling, or internet is completely down, and you know that if I grade something, that says that's done, so I cannot go back to it, then that's the one you drop justifiably. If, for example, you have really struggled through something because you have other assignments and you missed this one, that's probably okay. But do not come with an attitude that this is today when I watch The Walking Dead, so therefore I'm going to skip the assignment. That's not good, honestly, okay? Albeit I'm a fan of The Walking Dead, okay? Does this make sense to you guys? That's Wade's question. Okay, so let's get into the topic then. So this is chapter 11. Chapter 11 is the atomic nature of matter, okay? Chemistry is actually a branch of physics, so don't let anybody else fool you to think that chemistry is not physics. It's started that way, so chemists are really specialized physicists, no more, okay? Although probably they think, some of them don't think so. What was the... Okay, again, if something has been graded already, I cannot go back to it. It's really, if I do that, it's going to be a problem down the road. I mean, we will be doing the final and somebody is thinking, okay, how about homework 1? Can I submit it now? So at some point we have to make the cutoff. So what I'm saying is the following. Usually there is a deadline. I try to go by the deadline. But if I give a day or two when I grade the assignment, or sometimes even a week, then you have that window to operate. But do not think that it's going to be a week or 3 days, depending on when I have time to go around and grading things. Submit your work. If I grade it and you get no mark for it because you did not submit it, that's it. It's done. So if the assignment is still due, take advantage of that. Go ahead and submit it. Okay. It was a private question. I'm trying to answer it in general so that everybody benefits from it. Okay. Okay. So this is the topic of the day, again, the atomic hypothesis, okay? And this, again, the Greeks are known for their philosophical approach, so the idea of the atom is not new, so, but it was a theory. And then later on, we came up with more sound argument for the atom based on observations. So that's basically the whole idea with it, okay? We will try to discuss the how the atom is structured, okay? And then some models also. There are some models, especially if you take chemistry, introductory chemistry, you would think that the atom had this specific structure, but that's just a model, a representation of the atom. So here is basically the model. You have a nucleus where a bunch of particles, mainly protons and neutrons, sit together. Smaller particles than the nucleus. They constitute the nucleus. And then orbiting around it are the electrons, okay, and paths. But this is just a model. First of all, for one thing, the electrons do not have paths. They do not have positions, okay? So it's an electronic cloud more so than actually a proton. And electrons. And electrons are not specific points in space, okay? So they are distributed in space. But that's really a model, and that's what we're going to go with. This is our introductory course. So the atom is made up of a very, very small center where the protons, the nuclei, and basically all the nucleons, namely protons and neutrons, are situated. And then around them, very, very far away, extremely far from the proton, is where the electrons basically live. So if you take this one to scale, it's really not anywhere near where it should be, okay? So if you are a particle trying to migrate toward the proton, toward the nucleus basically, and you leave the atomic cloud, by the time you are very close from the center, which is the size of this nucleus, this would be about 10,000 times further away. So very far away, the electrons from the nucleus. So sizes when it comes to this one are comparable to the sizes of the solar system, basically. So the sun, albeit it's huge, and it's the core of the solar system, again, sits in the points somewhere on a focal point. All the planets orbiting it. In orbits, if you do really calculate the eccentricity of all of the planets, you will find them not too far from zero, with the exception of probably Pluto, which is very high eccentricity. I think Mars also have a high eccentricity, but the Earth and other planets, they're actually 0 point something. So they're more or less very close from from circular paths, actually. Then flattened path with a low eccentricity. That's the value you're supposed to calculate in here. So more or less similar to that, except this is the planets. The distance between these distances are huge compared to the size either of the planets or that of the sun. For example, the sun's radius or diameter from end to end is about 1.5 million kilometers, which is big. 1.5 million kilometers is a huge distance, okay? About 1 million miles. It's a lot of size for the sun. But compare that to the distance between the Earth and the sun, which is 150 million kilometers, or 93 million miles. It's still 1% of the overall, okay? And 1% is not representative, as I said before, because the nucleus and the proton and the electrons, they are about 10 times 1% of a 1%, if you wish. So it's even smaller than that. So the scale is it's an approximation, but not correct. Okay. So the emptiness, if you wish, in the case of the atom is far more greater than that of the solar system. But it's an empty space nonetheless. For the most part, there is an empty space in the atom as much as, or probably more so, than that of the solar system. Okay. Then we'll talk about the elements. The elements are basically a single atom structures. Okay, like for example, all of the periodic table are what is known as the elements, and that is actually the next topic, which is the periodic table, due to Mr. Mendeleev, who noticed that there is some patterns, and he put all of the elements, the known elements, in there, and people start to thinking, hey, maybe there is something missing in here, maybe we can make it. And sure enough, we know of 115 elements now in nature. Some of them occur naturally, and some of them we were able to build them in the laboratory, to make them in the laboratory. So that's basically how this works. So we'll talk about the periodic table, which is used extensively in chemistry because it turns out the chemical properties of all of the elements depend on their position on the periodic table. If you happen to be on the very far left, you have metallic properties. If you happen to be on the very far right, you don't have any, you are an inert. You don't participate in any chemical process because basically the gases there, they are saturated in terms of the electrons, so they don't accept or take, they don't give or take any more electrons than what they are, so they don't participate in any chemical. They're called noble gases or inert gases, okay? And anywhere in between, there is all kinds of chemical properties, and it's determined by basically the outer shell of this elements, depending on where they are situated in the periodic table. So for chemists, periodic table is probably the most important thing. They cannot leave home without it, okay? It's their F equals to MA, if you wish. It's really their bread and butter is that one in there. That's basically how they they survive. I mean, they cannot survive without it. Okay. Then we talk about the relative sizes of the atoms. It turns out that the more electrons you have in there, the more protons come into play, the greater the attraction, and that's due to electrostatic phenomenon. Basically, the charges attract one another. Negative charges for the electron and positive charges for the protons attract one another. So the atom shrinks in size, albeit it's growing in mass, so its density gets higher and higher, okay, per atom. But technically, you cannot get them very close because then starts to repel. Other phenomena come into play and they prevent those things from collapsing onto one another, okay? And that's the reason why actually this model of the solar system doesn't work, because of the fact that charges, when they are moving, one of the things they do is they radiate energy, they emit energy, and if they do so, then we have a problem. They should not be stable, okay? So the model is really a model, no more, okay? It's not real, it's an approximation, if you wish, first order approximation. Then we talk about isotopes. Isotopes turn out to be similar, basically, chemically the same compounds, namely they have the same protons and the same electrons, so they do the same chemical processes. However, they have the same chemistry. However, they have different physics because they come with different masses. They have different neutrons. So one of them is heavier than the other. So you can throw them, for example, in a centrifuge, and the heavier one will have more inertia than the lighter one. So you can separate them using physical processes because chemically they are the same, identical. Uranium-235 and uranium-238, they're the same chemistry. Both of them, they do the same chemical processes. But uranium-238 has extra three neutrons, which makes it heavier, okay? So you can separate them using physical processes, using basically the principle of inertia. And then we'll talk about compounds. Compounds are not like elements. In a sense, we have different elements combining and making a new compound. Case in point, for example, water. It's made of two elements. It's made up of a hydrogen and an oxygen combining in an H2O, and now you have the water molecule. Same thing, for example, in the case of sodium. I mean, sodium and chlorine, they both combine to make salt. Neither chlorine nor sodium is salt. So do not try to make your food taste better by adding chlorine to it and sodium to it, because that's not going to do anything. You have to add their combination. So in other words, the compound is different from its individual components. As a matter of fact, hydrogen is a gas, oxygen is a gas in room temperature, but when you put them together, they become a liquid, water. and it has completely different physical properties. For example, it's boiling temperature, it's freezing temperature. It has completely different properties when it comes to their behavior, including chemical properties. So a compound, albeit it's made up of different elements, its properties is different than that of the individual elements that it makes it. And this is as opposed to mixtures. So a compound basically is that it's a chemically bound elements. They bound together and they become a new structure, if you wish, new substance. Whereas a mixture is just a mixture with no chemical bonding, and that is, for example, the case of the air. Air is mainly nitrogen and oxygen basically floating with the given proportions. They are not interacting with one another chemically, but they are in the same mixture together. Okay. Then we talk about molecules, and then we talk about antimatter. Antimatter is a very, very unstable kind of matter because of the fact that we have matter. Like, for example, if I have an electron and its anti-electron, which is called the positron, those two, if they coexist in the same space, they will basically combine, and they will go poof. They will cancel each other, and basically you end up with just radiation. You'll end up with just light. Basically, their masses will cancel, and you end up with nothing. Protons also you can make in the laboratory, at least antiprotons, but they're also highly unstable because of the fact that they have the same mass as the protons, but their charge is different. So when they come in, they collide, and they also go in smoke. They're extremely highly unstable, all of the antiparticles, antimatter, and I had a chance to visit one of the nuclear labs who were doing experiments on these things, and they use magnetism to confine, at least to temporarily hold the antimatter that is formed. Okay, but then when it meets its counterpart, it's going to be annihilated. That's going to be canceled basically, and you'll have a lot of energy coming from the nuclear reaction. That is not the same thing as dark matter. Okay, and dark matter is today's topic in terms of the discussion. Okay, so dark matter, first of all, it was discovered by Vera Rubin when she was observing doing measurements actually on the speed of the stars around the galaxy, and she noted that they all have a regular behavior, well-behaved behavior. I mean, as you move away from the center of the galaxy, the stars move faster and faster and faster because it's a very well explained with the mechanics of Mr. Newton. There is no problem with that. The minute you exit the galaxy, she expected the speeds to start to drop now because she accounted for all the matter that is in the galaxy. So there is no reason for the velocity of the stars to keep on increasing. What she noticed, though, is that the velocity did not decrease. It decreased a little bit, and then it went up, then decreased a little bit, went up, and then stayed steady. So the only explanation she had for that is that there is matter that we can see, matter that we can't account for. And that is how dark matter was discovered. It turns out dark matter is a big player. I mean, you're sitting in your rooms right now and you think that you're alone. Think about it. Your bed, your chair, your desk, your computer, your cat next to you, whatever you have, a dog, your cup of water, everything else in the house, including the kitchen and the sink and everything that go with it, is a fraction of what is out there. Okay? It's just a small fraction of where you are right now. Okay? That's kind of scary a little bit. Everything that you can think of surrounding you right now makes up about 4% of everything out there. Okay? 23%, which is far more than you are, more than about 5 times of all of the stuff that I mentioned before. And maybe I forgot the remote control and other things that you have laying around there. Okay? All of that is just about the one, the 1/6 of everything in your room and where you are right now. So as you move your hand like this one, you are encountering a huge amount of dark matter. That's a fact. That's what Vera Rubin has discovered, basically. Okay, that's a fact. That's not sci-fi. Okay, but we don't interact with it. We don't feel it because it doesn't have protons and electrons the way that we see them. It doesn't have electrons, at least. That's why we can't see it. That's why we can't hear it. That's why we can't touch it. That's why we go through it like knives on, I mean, hot knife on in the butter, basically, and they go through us exactly the same thing. So we don't feel it. So when you do like hand like this one, there is a bunch of dark matter where you are right now. In addition to that, there is dark energy. Okay, dark matter is about 23% of everything out there. Oh man, 23%. Dark energy is about 73%. Dark energy, we know it exists because one of the things, the indications for it is the universe is expanding. Okay. That combines to 96%. So we are here in this class. Today is September 29th, and we're wondering about the missing 96% of the stuff that is out there. What is it? We don't know. Okay. We know it exists. There is every evidence for it that it exists, but we don't know. In the same room, probably there is another group of dark matter students sitting with their dark matter instructor, wondering about the missing 4% because they can't see it and they cannot touch it. Okay, that's us. Okay, so we're here, guys, if you can feel us. Okay, I mean, there is probably a good reason now. There is a lot of research on this topic right now, so maybe there is an explanation for it, that it's made up of a different kind of quarks, and there's a lot of research and work on it. So this is a quote from Mr. Feynman, who's known to be the best teacher of physics of the 20th century, at least. And he said that, oops, did I skip that? All things are made up of atoms, little particles that move around in perpetual motion forever. Okay, that never stops, attracting each other when they are very far away, where a little distance apart, I'm sorry, but repelling one another when they're squeezed into one another when they come closer. There is all kinds of reasons why they should not come together. One of them is so-called Pauli principle, and another one actually is at least for the yeah, that's basically the reason why you cannot push any more two electrons in the same state, and they are actually at least for the electrons and the protons and neutrons. Okay. So the idea of, or at least the original hypothesis for the atom dates back into the times of the Greeks. Of course, Aristotle thought the air and the earth and fire and water are the elements with which everything is made. But of course, that's his hypothesis. It turns out the earth and the air and the water, at least, and including the fire, which is another state of matter, which is plasma, are made up of tiny particles. The Greeks, again, theorized that if you take a rock, for example, you cut it in half, and you take the half and you cut it in half, you take another half, cut it in half. Ultimately, you're going to reach a point where you can cut no more, and that is where the atom is. Okay, so by the 1800s, John Dalton basically proposed the idea again of the atoms. Okay, based on his observations for the study in thermodynamics and heat and things like that, and gases and things like this. Now, we believed, at least up into the beginning of the 20th century, that this is the smallest thing there is, that the proton is the smallest particle that you can think of, and the neutron also has a similar properties, and the electron is actually smaller in size because it has less mass. So it's probably smaller in size physically, but that's it. It turns out that this picture is not complete, and by the 1960s, 1970s, a new model emerged, where what is called the standard model, actually, that this stuff is made up of their own particles, okay, quarks, and we're going to be talking about quarks. And quarks, there are so many of them, we couldn't call them positive and negative anymore. So we came up with different names for them, okay, up, down, and all kinds of, basically with color and taste and all kinds of things, okay. And it's just naming because they carry with them different charges, different spin properties, and different basically physical properties, different masses. That's why they have different names. Okay. Again, Mr. Brown, Robert Brown, came up with made an observation. He was looking at some microscopic particles with the and fluid, and he noticed that they are basically moving in some sort of what looks like it's a random motion. Okay. If you have ever seen a drunken man moving, that's basically similar to that. Okay. As they are falling in a liquid with high viscosity, for example, due to gravity. Okay. They follow this zigzag pattern. Sometimes they go in, down, up, and down, but on average, they go down. Same thing with the drunken man, okay? When he leaves the bar, he makes one step forward, two steps back, step forward, step back. And if he's doing a linear motion, he will end up home at some point, okay? But each time you cannot really predict which way he would go, okay? So that's similar to it, more or less. So the explanation for it in here, that these particles, these microscopic particles suspended in the fluid, must be hitting particles that we can see, and that is basically the hypothesis that Mr. Einstein took, and he was able to explain that, and that is where the evidence for the atoms of the fluid are basically touching this so-called, I mean, we cannot see the atoms because they are even smaller than this particle suspended in the fluid, and that this one's in here, there, as they're colliding, each time they bounce up, and down, and that's where the hypothesis of the atoms came in. Then Mr. Boltzmann did another calculation in around the end of the 19th century, 1880s or something, where he basically explained the concept of pressure, concept of in a gas, using the same ideas, similar ideas, that the gas is made up of tiny particles, and he was able to explain the ideal gas law, which we will see in the next chapters. And his work later on, people basically made fun of him, and he unfortunately committed suicide because of the peer pressure, because people were making fun of him. Hey, Mr. Boltzmann, look at these tiny particles that you think they exist in the air. I grabbed some, here they are. Sure enough, of course, he was right. Mr. Brown was right. Mr. Einstein was right. And the atoms now are common knowledge, okay, based on what we think is the structure of the atom. So sometimes peer pressure can play a really negative role on people. So you have to really, if you believe in something, pursue it. Maybe you are into something, and okay, and ignore what the critics are saying, because sometimes they don't know what they are talking about. Okay, turns out that they are the fools, not Mr. Boltzmann. Nowadays, when people, at least physicists, when they go to Vienna, one of the things they do is go and visit at least his tomb, which is in Vienna. Okay, in Austria, to honor him. Okay, this is basically how the atoms are. It's an incredibly tiny particle. It's very, very small. Okay, it's of the order of 10 to the negative 10 meters. It's very small, 10 to the negative 9, the order of a nano or an angstrom. Angstrom is this distance, okay? So it's a very small distance. An angstrom is 10 to the negative 10 meters. So it's 0 followed by 9 zeros. I don't know how many zeros I wrote, and then a 1 in there, okay? So it's very small in size. Meters, that is. And there are a lot of them. In 1 mole, for example, which is typical measurements for a gas, you will have an Avogadro number of them, which is 10 to the power 23 of them. So it's a huge number, okay? So that's just 1 mole. So imagine how many moles there are in the air, for example, and all the particles in the universe. So you have a huge number. I mean, it's a big number, okay? Of course, they are in perpetual motion, and they existed ever since the universe basically came to be. The universe immediately after the Big Bang was super hot for the atoms to exist, but then immediately after 300,000 light years, after 300,000 light years, 300,000 years after it was the Big Bang, the first basically molecule starts to form, and they're actually hydrogen, and then helium. They formed immediately from the first, not molecule, the first atoms basically formed at hot temperatures. And ever since that, stars were able to produce the rest of the elements, okay? All of the other elements, because the Big Bang only produced 2 elements for us. So initially the universe had only hydrogen and helium in it, okay? atoms only, not molecules either, because it was too hard for that. And that did not actually exist until only 380,000 years after the Big Bang, because it was too hot at that point. So ever since that time, these two elements existed, and immediately thereafter, after the stars formed, they started making the rest of the elements. So all the entire basically laundry of elements, the 190 or so of them that we know exist in nature, they were formed a long, long time ago, okay, by mainly the stars, okay. The Big Bang didn't only produce these two. Okay, maybe traces of other elements, but this is the, I mean, this is it, okay. And the ratio that the Big Bang made it is 75% hydrogen and 25% helium. So which of the following are incorrect statements about the atoms? Atoms are smaller than the wavelength of light. This is true, because 10 to the power, I mean, light is of the order of a few hundred nanometers, or smaller, bigger than the slightly less than a micrometer, which is 10 to the negative 7 meters, actually, to be more specific. This one is even smaller. Okay, it's about 1,000 times smaller than the wavelength of light. Okay, then atoms are mostly empty space. That is true. Atoms are perpetually moving, and that is true. If they don't move, then we have a problem. Then they collapse on one another. And atoms are manufactured in plants and in humans during pregnancy. Is that true statement? The last D. I know A is correct. I know B is correct. I know C is correct. Okay, thank you, Jeffrey. Okay. Yep. So yeah, I mean, it doesn't. It's nonsense. I think the author in here trying to play games with us. Okay. So hopefully this is nonsense. So this is the correct answer, because they're asking which one is not true. This is incorrect. Okay. So this is the correct answer because it's asking the incorrect statement in here. Again, this is an actual picture by microscope. Again, just to argue the fact that it's so small that you cannot take a picture of it with light, because it's even wavelength is smaller than that of light. Again, I already mentioned the fact that the atom is made up of a nucleus. Inside the nucleus, there are so-called nucleons, and nucleons include both a proton and neutron. Neutron has no charge, basically, and protons has a positive charge of 1.6 times 10 to the negative 19 coulombs. Okay, that's the charge of a proton. Quarks, they make up these ones in here. They're even smaller particles, and in the standard model, it gives you exactly the calculation for it. Okay, so that is the nucleus. That is the inside of it. Outside of the nucleus, you have the electrons. Okay, so refer to the atoms. Refer to the particle type of that makes a substance. Elements composed of only one kind of atom. Okay, so there are 90 of them known in nature, 150 in total. So the rest must have been produced in lab, and they're unstable. They don't stay forever. So because they have radioactive behavior, they go immediately and disintegrate and go to different states. Okay, especially the heavier ones. So sometimes when we say atoms, we mean also the elements. In chemistry, especially in organic chemistry, they deal a lot with this kind of elements. Okay, oxygen, carbon, hydrogen, nitrogen, and calcium. Okay, if you are into astronomy and you examine, for example, the structure of anything, you know, and you find oxygen, excuse me, in the form that we know it, at least abundance that we know it, is a signature of life. Earth, when it initially was formed, did not have much oxygen. It was plants that actually formed all of the oxygen that today we breathe. If we lived about 4 billion years earlier, actually 3 billion years before today, or even actually I think about 2.5 billion years before today, animals could not survive in that environment because of the lack of enough oxygen. So it turns out that life took a long time through the plant stage to form the oxygen for the rest of the other basically living organisms other than animals to start to breathe the oxygen. So oxygen is a signature again of life if we find it in the form that we know it on Earth, namely in the form of gas. Okay, it existed in the Earth initially, but it existed mainly in rocks. Again, carbon, hydrogen, nitrogen, and calcium, these are the compounds of all of the living things, at least life as we know it on Earth. Okay, so this is the elements that exist in nature. It's life. Okay. So again, we talked about the periodic table. Periodic table is characterized by the group and the period. Okay, the group in here is talking basically how many electrons in the outer shell. Basically, all of these ones they have one. This they have two. This they have three, and so on and so forth. Okay, and there is a specific structure that need to be followed. Okay, for them until you come in here, which are the gas inerts. Okay, all of this are the so-called metals. Some of them are more metallic than others. Okay, all of this are the so-called non-metals. Okay, and this one are transient, or what is it, metalloid elements, basically, especially these two, germanium and silicon and germanium. I'm sorry. Okay, they are extensively used nowadays in almost every device because they are the basis upon which modern electronics basically revolves, and they are the basis with which you can have semiconductors. Semiconductors, they are conducting like sometimes metals, but sometimes they don't conduct like non-metals. So they are either that and the other. And silicon and germanium are these two elements. And if you have heard of the area near San Francisco, Silicon Valley, is because of the this stuff in there. Okay, so again, they have a lot of interesting chemical and physical properties in terms of their chemical properties. For example, how do they combine? Do they release energy or get energy? And all kinds of processes involving living organisms and things like that. Also in terms of physical properties, in terms of their conductivity for heat, in terms of their conductivity for electricity, in terms of different behavior that is interesting for the elements in there. So the periodic table is not just interesting and important for chemists, but it's also for physicists too. Again, the diameter, and I already mentioned the reason why, is because of the electrostatic forces between the protons and mainly the protons and actually the outer shell of the electrons. For the hydrogen, for example, atom, it has only a single proton and it has a single electron. Okay, so in this case, there is an electrostatic force that keeps them this way at this distance. Now you take the case of the hydrogen atom now, helium atom, you have two protons and two electrons. So the attraction is greater. So all of a sudden now the atom shrinks a little because there is more attraction between the nucleus and the electronic cloud. Same thing. And that's why you see the sizes now are getting smaller and smaller because of this electrostatic effect. Okay. Lithium has more protons in it, 3 protons and 3 electrons, versus what is this one, neon. So you're gonna go in here 1. So this one has 2, 4, 5, and so on and so forth. You can move on until you find the exact number of them. So now you have a bunch of protons, a bunch of electrons trying to pull on each other, and they collapse and makes it, but it's heavier. It has more stuff in it. Okay. And the same thing, it goes for all of these lines in here. So as you look at it from here to there, the size of the atom starts to get smaller and smaller. Okay. So if somebody asks you what's the smallest size atom, it's actually helium. Okay. It should be helium, not hydrogen. Physical size, that is. Ions and isotopes. An ion is an atom deprived of an electron or has an extra electron in it. So if it's deprived of an electron or electrons, it's positively charged. If it has an extra electron or electrons in it, then it's positively charged. An isotope, as I mentioned before, has the same number of electrons and protons, except two isotopes, for example, except the number of neutrons are different. Case in point, for example, uranium-238 and uranium-235. They have the same number of protons each, but they have a different number of neutrons. So that's basically the distinction between the two. Their chemical behavior is identical. They have the same chemistry. Okay. Their physical properties are different. Case in point, uranium-235 is far more useful than uranium-238 in terms of nuclear reactions. One of them is active, the other one is basically doesn't do much. One of them you can make nuclear bomb out of, and that's why you do uranium enrichment, is to make it more active than the one that is more nuclear active than the other one. So this behavior, the identical behavior here, refers to the chemistry because they have the same electrons at the end. So protons in nucleus match the number of electrons when it's neutral, of course, okay? But the neutrons not necessarily. Actually, neutrons are needed for some other purposes. If you were to strip a nucleus out of all of its neutrons, it's not going to be stable, okay? So if you take, for example, uranium, you have 92 protons in it, okay? Now you have a bunch of positive charges that they want to repel one another because of the electrostatic force, but the nuclear force will glue them together, but the nuclear force acts only very short distance. So this proton and this proton will attract one another because of the nuclear forces, and they will overpower the force of the electrostatic, which is repelling them. But this one and this one, they're too far apart to really have any kind of nuclear interaction whatsoever. So they will destroy the atom. It will not be stable. So what happened in this case, you throw in more and more protons and neutrons. And neutrons in this case, what they do, they go in between them and they glue the entire nucleus together. Okay? Because they don't play the electrostatic game, but they play the nuclear game. They fuse, they keep the atom from going completely unstable and basically disintegrate. So that's the usefulness of the neutrons. They play a very important role in terms of stability of matter. Without them, we would not be here talking about these things. Okay. Again, since they don't do anything in terms of chemistry, so you can have one more or one less, it doesn't matter. Two more, it doesn't matter. Okay. But they themselves are not stable, by the way. They themselves actually, they transform spontaneously into a proton and electron. So they themselves actually can cause trouble because they change the entire element from one to another. So if one of these protons decides to go radioactive and basically change from a neutron to now different charges where the electron is ejected, now this is a completely different compound, a different element, I'm sorry. Okay. So the atomic number of an element matches the number of the protons in the atom or the electrons. So the atomic number is basically the chemistry of the element. So how many electrons when it's neutral you have, okay? It's always the number of the protons. So that's the correct answer. So the correct answer is C, as a matter of fact. So a nucleus with a 44 number of 44 mass, okay, I mean an atomic number of 44, but an atomic mass of 100. So in this case, 44, I have to subtract it from 100 to find the number needed to bring its atomic mass to 100. This is the masses of course, a proton, which is by itself 10 to the negative 27 kilograms. So the correct answer is 56. Again, I talked about compounds and mixtures. Compounds, they have a chemical bonding between different elements. Mixtures, no. Here are examples of molecules. Molecules are made up of different elements. They could be the same, like for example, the oxygen in the air, Okay, the ozone, for example, you have 3 of them, and this is, what is this one? Nitrate. So this is different elements in here. This is the water molecule, and this is methane or something like that. No, this is ammonia. I'm sorry. Yeah. Okay. Chemical reaction is a process in which atoms rearrange themselves and basically. Did you took chemistry, guys? Didn't you? Anybody? No. Okay, some of you did. So this is not too foreign to you guys. Okay. Again, I already talked about antimatter. Antimatter is the same basically stuff, except that it's matter to begin with. So it's part of the 4% I was talking about. It's not the 96%. It has nothing to do with dark matter. So antimatter is matter. Okay. So that is but it has different properties, so it cannot exist in our environment. So basically, it's so highly unstable because it meets matter and they cancel one another. Okay, the well-known one is positron for the electron. So the electron has a negative charge, the positron has a positive charge. They have the same mass though. Okay, an antiproton actually has a negative mass, whereas the proton has a positive mass. So this is an antiproton, and this is a proton. This is an electron. This is an anti-electron, but it has a name. They call it a positron. Okay. Dark matter already insinuated into how it was discovered, and it was discovered by Vera Rubin. And it makes up about 23% of the universe. Again, this is the behavior that you expect. This is the radius of the galaxy. Any galaxy, it doesn't matter. So when she started looking at our own galaxy. Then okay, let's me check Andromeda. The same thing with Andromeda. Then any galaxy, as a matter of fact, has the same behavior. So these are stars and how fast they move, okay? And this is how far they are from the center of the galaxy. They're very close from the center, they move slower. And as you expect this behavior, once you reach this point in here around the halo of the galaxy, so this is the halo of the galaxy, at that point, the assumption is, at least Newton's laws of motion state that this velocity needs to drop with distance. There is no need for them. Like, for example, the planets. We know that the Mercury moves super fast. The year on Mercury is a lot less than the year on the Earth. Venus actually year is shorter than that of the Earth because it moves faster than the Earth. Earth is 1 year to go once around the sun. Mars takes almost 2 years to go once around the sun. And then Jupiter, which is the next, takes about 12 years to go once around the sun. So as you move further away from the sun, we know the behavior. The planets move slower. The same thing is expected for the stars when you take them with the galaxy. She did not find that. This is what she found. She found that they go like this and they stay stationary, indicating that this is not correct, that there must be more mass actually in here that we can compute. And when she worked the math backward, this is where the number 23 came there. 23% is of more mass than what we are, than the actual mass that we have in here. Now, what keeps the universe expanding, the forces that keeps it expanding, it's called dark energy because we don't know what it is. The word dark in here doesn't mean that it's black or anything like that. We don't know. It's our ignorance. Okay? So the word dark in here reflects our lack of knowledge, if you wish. Okay? And we're trying very hard trying to understand what dark matter is and what dark energy are, because we don't know. Okay? So if you add 73 plus 23, so the rest of us are the 4%. What is the rest of the regular matter and everything else is about 4%. And that is the topic of today, okay? So I want you guys to reflect on this point, okay? And if you can find the author, her name is the initial person who did that, and try to connect it to the previous chapter where we discussed the the motion of the planets and all of that. So, okay. So let me give you her name. Okay, the way I was going to spell it to you guys, but I didn't want to misspell it. That's the name of the original person who basically was behind the discovery. And she had quite a story, so it's really an interesting story that probably it's a good idea to ponder about it. And she actually talks about it herself, is the fact that she struggled with her discovery because, for one thing, she's a woman. Okay, I think she passed away not too long ago. I think this year or last year or something like that. And she, not only that, but she's going against the biggest name in science and physics at all, namely Newton himself, because the theory of Newton expects certain behavior, and she didn't find that. So she hesitated a lot, and sure enough, she was basically dismissed by all of the men basically who dominated that field of astronomy because of her discovery that, hey, you're talking nonsense. I mean, until later on, her observations were confirmed, and sure enough, dark matter is now an established fact. So I want you to look at this, if you can find the work on her, okay, what she did, and tell me about this dark matter in here, and try to explain it in your own words. So that's the assignment for today. You guys understand? Okay, thank you, Jeffrey. Okay, so let's continue. Now we're done with this chapter, actually. We're done with it. So just basically the fact that it's today is top priority, and maybe we'll know more about it in the future, in the near future. Actually, there's a lot of papers coming almost on a weekly basis nowadays on this topic, okay? So let me stop sharing that screen quickly and share with you the question. Reflect on dark matter and its discoverer. There is a lot of prejudice, discoverer, in science, and she suffered that prejudice herself, okay? And she talked about it herself too. Again, if you're not of a certain background, sometimes you're not taken seriously. And she was not initially. And she herself, actually, before going forward, she struggled with it herself because she was hesitant because she's a woman in a man-dominated field. So she was trying to be as accurate as she can be, trying to satisfy all the critics, and before going forward, she wanted to make sure that her observations are correct. Okay, so, and that's sometimes a challenge. If she was not a woman, probably she would not hesitated initially and published her work, and probably it would have been accepted much quicker than she did. But at the end, she was right, and now recognize her at least for what she did. Okay, so let me share with you the next week's topic because it's relevant for you guys for the lab, and since we have a little bit of time, so I want to talk about that one. And since we have a lot of topics to talk about for next week, or next week, Thursday, and that's the different states of matter. We're going to talk mainly about solids, liquids, and gases, and also we'll talk at the end about plasma, okay, which is a different another form of matter that we can talk about in here. Of course, we will see exactly the distinction between these three different kinds of phases. Basically, that's what they're called. But at the end, I want to bring your attention to the pressure, the concept of pressure when we do liquids and gases, when we do fluids in general. So fluids include both gases and liquids. Okay. And fluids, they're characterized by pressure. Pressure is a very easy concept to understand, which is force over area. The bigger the force, the smaller the area, the bigger the pressure. The pressure is measured in Pascal. If you like, it's measured actually in Newton per meter squared, but that's also has a name for it, Pascal. For example, right now, all of you are sitting in about 100,000 pascals. That's the atmospheric pressure that we feel on a day-to-day basis, okay? That's a concept that we can see in all the fluids. And again, even metals, they can basically be under pressure You can compress them, or you can put them under tension. So that's similar kind of a pressure. So that's basically, and depending on the solidity, depending on the physical properties of the solid, you can have elastic behavior. The solid can go back to its shape, or it can deform. Okay, so that's. But for liquids, they don't have that. So again, you're going to have all kinds of, or fluids in general. Now, if you take a fluid, it doesn't matter which one. Liquid, water, for example. It's a good example, water. And let's put it in a container. And let's say, for example, this is water, okay? Of course, for my visual, if I put it on a desk and wait for it for an hour, I would think that there is nothing going in the water. It's stationary. It's not going anywhere, okay? Water has specific density. The density of water is 1 gram per cubic centimeter. That means how much water I have for each volume that they have. For 1 centimeter cube, they have 1 gram. For 1,000, for 1 basically cubic meter, I have 1,000 kilograms. So that's the proper sum of the properties. Now, if I put a food coloring, for example, in the water, I would see initially that the food coloring will travel throughout the water, but then it stays stationary. The water now is colored whatever that food coloring is. So I assume that the fluid is going nowhere. It's not in state of motion. It's not dynamic. It's static. It's not going anywhere. So I take the following rationale, the following argument. I'm going to take a cross section, a cut if you wish. My pen is stopped drawing. Okay, imaginary one inside the fluid, and I argue the following. That fluid must have a weight, must have a mass, and the mass is given by the density times the volume. So it has a mass, and it's sitting on Earth, so it must have gravity, it must have weight. This is the weight of that imaginary cut. Of course, you're looking at the cup, and you're thinking a small volume in the cup where the food coloring is, it's not going anywhere. So you know it's stationary. But you know the force of gravity is acting on it downward. So there must be a force to keep that water from falling, from that imaginary cut from falling. And that force is exactly what is needed to balance it. Okay? So what I'm going to say in here is, this side and that side is irrelevant because we don't have a force of gravity on the sides. We have it downward. So what matters is the upward motion. So what I say in this case in here, that there is a pressure from the bottom, from the fluid, and pressure from the top, so that the difference in pressures is exactly what is needed to keep the fluid from falling. In other words, there is more pressure from the bottom than pressure from the top to keep it from falling. And the combined effect of the lower pressure, which must be higher, by the way. So this is the lower pressure. And the top pressure, which is smaller, then that must be enough to cancel the weight of that imaginary fluid. Otherwise, the entire fluid will go to the bottom of the cup, and it would not have this level. Everything will fall to the bottom, and it's not. That is what the buoyant force is, the difference in pressure. So that is where the buoyant force is. That is what is responsible for holding, basically. Now, if I don't use water and I bring another object, okay, and put it in, that object will sink, of course, if it has higher density, but it's going to feel lighter because of the same problem, because of the same thing, which is the buoyancy. Okay, so I want you guys to think about this. This is for next Thursday. This is also for the lab for Physics 11. So that's the entire lab. Basically, the idea behind is the buoyant force and its source, which is a difference in pressure between different heights in the same fluid. Okay, the bottom exerts more pressure than the top one. As a matter of fact, if you think of the entire surface in here, there is no pressure from the fluid at all on the top. All the pressure is just coming from the bottom. If you are just on the surface of the fluid and then somewhere else. Okay, so and the pressure actually is given by a formula, which is equal to the density of the fluid times the depth. So this is the density times the depth times the force of gravity times not the force of times the g, which is 9.8 meters per second. So that is actually the density. That is actually the pressure. Okay, and that is how we explain buoyancy. Okay, you know what you have in terms of reflections, so hopefully you guys will look into the story, okay, and ponder about the fact that we are only 4% of everything there is, including your kitchen and everything else in your place, including the sink and the kitchen and everything. And that's the topic for today. Okay, it's not the questions that are related from this. Any question for me? And don't forget you have a second part in the assignment. I actually extended the discussion from last week just to make sure that you guys, first of all, do the assignment, and second, respond to other people. So please do that, okay? Okay, I'll see you guys Thursday at the same time.